Let's be real for a second. Have you ever heard the terms probability mass function and probability density function? Kind of nodded your head like you knew what was up, but secretly had no clue? You are definitely not alone. So let's dive into this, because getting the difference here is one of those aha moments that unlocks how we see data everywhere. It usually starts with a question that looks just like this, probably ripped right out of a statistics textbook. Hey, what's the difference between a PMF and a PDF? And look, this isn't just about getting a good grade. The answer to this question is really about learning to see the two totally different ways that data can describe the world around us. So here's how we're going to tackle it. First, we'll look at the two different worlds data can live in. Then we'll get to know the hero of each world, the PMF and the PDF. After that, we'll put them head to head to make it super clear. And finally, we'll see why this whole thing is way more important than you might think. To really nail this, we have to start right here. See, the choice between using a PMF or a PDF isn't just a random preference. It all comes down to the kind of data you're dealing with, or as we're going to call it, the world your data comes from. And really, there are only two of these worlds. On one side, you've got the world of countable things. We call this discrete data. Think about it. The number of cars in a parking lot. You can have 10 cars or 11 cars, but you can't have 10 and a half cars. The values are separate and distinct. Then on the other side, you have the world of measurable things. That's continuous data. Take a person's height. It could be 180 centimeters, or 180.1, or 180.1125. Between any two heights, there's always another possible measurement you could take. All right, so let's take a trip into that first world, the world of things you can count. This is the home turf of the probability mass function, the PMF. The fancy term for the data here is a discrete variable. It's just a formal way of saying what we were just talking about. The possible values are like rungs on a ladder. There's the first rung, the second rung, but there's nothing in between them. And this is where the PMF comes into play. Its job is super simple, super direct. It tells you the probability that something is exactly a certain value. Now, I want you to burn that word exactly into your brain. It is the key to everything. What's the chance of rolling exactly a 3 on a die? A PMF will tell you. And nothing makes this clearer than just rolling a standard die. I mean, it's the perfect example of discrete data, right? Your only options are 1, 2, 3, 4, 5, or 6. That's it. You can't roll a 2.7. And this is what a PMF looks like in action. Each possible outcome gets its own bar, its own chunk of probability mass. The probability of rolling exactly a 4 is 1 out of 6, or about 16.7%. Same for a 5, same for a 6. Each individual distinct outcome has its own specific measurable probability. Okay, time to switch gears. Let's jump over to the other world. We're leaving behind those neat, countable steps and entering the smooth, unbroken worlds of measurable data. The rules are totally different here, so we need a totally different tool, the probability density function, or PDF. The data in this world is called a continuous variable. Think back to height or temperature. Between, say, 175 and 176 centimeters, there is a literal infinity of other heights. You could have 175.1, 175.11, 175.111, and just keep adding decimal places forever. Now, this idea of infinity leads us to a really mind-bending question. If you can be infinitely precise, what's the probability that someone is exactly 180 centimeters tall? I mean, down to the very last infinite decimal place being a 0. The answer, believe it or not, is basically 0. It sounds crazy, but think about it. If there are an infinite number of possible heights, the chance of you landing on one single, specific, infinitely precise height is 1 divided by infinity, which is, well, it's so close to 0, it might as well be 0. Our old PMF trick of assigning a probability to an exact point completely breaks down here. So what do? We have to change the question itself. We have to stop asking, what's the chance of being exactly 180 centimeters tall, and start asking, what's the chance of being between 179 centimeters and 181 centimeters tall? We have to think in ranges, in intervals. And this is the absolute genius of the PDF. If you look at a PDF graph, the height of the curve at any point isn't a probability, it's a density. Think of it like population density. It's higher in a city than out in the country. To get the actual probability, you have to measure the area under the curve for the range you're interested in. The wider the range, the more area, the higher the probability. All right, we've been to both worlds, we've met the main characters, now it's time for the main event. Let's put these two ideas side by side and finally settle our original question. This table really sums it all up. Your PMF, that's for discrete, countable data. Your PDF, that's for continuous, measurable data. The PMF gives you the probability of an exact value happening. The PDF tells you the probability of falling within a range by looking at the area under its curve. But here's the cool part. Notice that with a PMF, if you add up the probabilities of all the bars, you get 1. And with a PDF, the total area under the whole curve also equals 1. They're just two different ways of saying that the probability of something happening is 100%. Okay, so you might be thinking, this is cool, but why does it actually matter? Well, it matters a lot, because this isn't just theory. This is about how we build models that actually reflect reality. Anytime we're trying to model something that involves counting, the PMF is our go-to tool. How many customers are going to show up in the next hour? How many typos are in this article? How many points will a team score? All of those are discrete, countable things. And the PDF? That's our tool for anything we measure. What's the probability that a stock price will close in a certain dollar range? How long will it take for this website to load? What's a patient's blood pressure? These are all continuous variables that can exist anywhere on a spectrum. So here's the bottom line. In data science, in finance, in engineering, in basically any field that uses data, the very first step is to figure out which world your data lives in. If you pick the wrong tool for the job, if you use a PMF for continuous data or a PDF for discrete data, your model will just be wrong. It's that fundamental. There's a great quote from the mathematician David Mumford that I think just perfectly sums this all up. The world is continuous, but the mind is discrete. We love to put things in neat, separate boxes. That's how our brains work. But so much of the actual world is this smooth, flowing, continuous thing. At the end of the day, PMF and PDF aren't just equations in a textbook. They are the essential building blocks we use to make sense of a random world. They're the lenses that let us see the patterns, whether we're counting things one by one or measuring the flow of change. So now we have the tools. The only real question left is, what do we want to understand next?